All right. Hello, everyone. So thank you for attending. So today I'm going to talk about our proposed project, real-time telemetry and observability for cloud operation and security. So I'm Alan Liu, I'm in the faculty in the EC department. We are a group of researchers at BU, including me and David Starbinsky, my colleague Ari Trachtenberg, also PhD students Ying Zhu and Jonathan Chamberlain. So today, in the cloud and edge settings, we are seeing a lot of compute and data-intensive applications. They are pervasive. For example, we have the big data framework like machine learning system, big data frameworks like Apache Spark, OpenAI models. We have the data center and network integration networks. For example, hosting your favorite service like video streaming and autonomous driving, extended virtual reality, etc. We also see Internet of Things that have big roles in all generating data and then running edge computing and federated learning. So across all these applications, I think we see increasing demand on security, cost, and performance. So with development of these applications, the entire computing stack is facing significant data challenge. So you can see here, right, for example, in the network infrastructure, we see the traffic grows massively. And in the platforms, for example, the cloud and containerized platforms, we see a lot of data centers and clusters and then generating a lot of system logs and metrics. Of course, in the different variety of applications I just mentioned, that you see the data generated each day. So across the entire computing stack, we see that this generated of the data needs to be monitored and captured for security and diagnosis purposes, for performance optimization, and for network management, etc. Right? So the key to enable the performance and cost and security efficiency, everything is relying on the observability of the systems. So here we're trying to propose our project that given these data challenges, we want to develop approximate telemetry systems. What I mean is, ATS is across its different system layers, including networking layers, hypervisors, virtual machine and containerized, that we already have an existing toolchain of telemetry. For example, in the networking side, we have DBDK to do high performance network processing. On the platforms and hypervisors, we can monitor the metric using Prometheus and Grafana to virtualize it. But the key missing piece is that they all store everything. They have to, run and linear scaling in terms of the data. So what we envision here is that given this data growth, we wanted to propose a toolchain of approximate telemetry, which we integrated this approximation techniques into different layer of the toolchain. For example, integrating DBDK to integrating into FDIO BPP, and then we want to turn this old type of time series data with symmetric monitoring into a real-time schedule-based inquiry and telemetry systems. So you might be a little bit confused what I mean ATS or approximate telemetry systems. So what I mean ATS is a telemetry system that can produce real-time and approximate queries results that by storing, processing, and computing less data. And also provide a high accuracy guarantees that, for example, some bounded errors with for example, 5% of errors that can still maintain the operational guarantees, right? So we can still generate highly accurate alerts and then, notify any changes in systems. And of course, we envision all this kind of telemetry that process using approximate way can give us several order of magnitude in terms of cost and performance energy trade-offs. And we really have high hope that it can address the very massive data growth across all the computing layers. So to realize this project vision, we have a few objectives, right? So we have two research directions to really fulfill this vision. So one is that it's not only an implementation of system issues. We also need to fundamentally think about the way we implement the telemetry. We need to bring in a lot of approximation algorithms, for example, like sketching algorithms, sampling, and smart sampling, randomization that can really bring down the processing cost or storage cost of processing this all kind of telemetry data. And the same side, we also need very smart techniques that can implement efficient system libraries that can work for systematic monitoring, can work for high-performance networks. So to combine this together, we will have the approximate telemetry systems, or ATS. So we really envision we build a practical and principled approximate telemetry system to handle the substantial system data across all the layers. Then you might be a little bit confused at here. How about our methods? What kind of method we're bringing, right? So as a system builder or system researcher, do we just need to implement this algorithm? Sometimes the algorithm is already there. The very smart Siri guy in Siri community already come with some algorithms. Is that our goal? Is just to implement them? I guess you already have, many of you already have the answer here. So it's very common for the system builder to implement an efficient algorithm that claims to be many times faster, many times resource efficient, but now it's not seen it in practice, right? So the fundamental reason we observe here is because of the mismatch between the system goals and algorithmic design goals, right? So it is not the case that the algorithm is wrong or Siri is wrong, but it's the case that, oh, we need to kind of bring in for example, the system requirement, like hardware constraints or performance requirement, really bring this into the algorithm side. That when the algorithms are developed, we need to reformulate the Siri goals and Siri modeling to really reflect the system requirements. So in general, to achieve the approximate telemetry system, we need to combine the system and Siri system magic. So one such example I want to introduce is, for example, in SICOM 19, we have a work called Nitro Sketch. It's coming only from a research prototype. Like we start from studying a virtual network switch called Open vSwitch, and then we want to bring in this approximate telemetry envision into that platform. And then we publish the paper, we talk to the maintainers of this software, maintainers, and we find nothing happening because the telemetry may not be a priority goal for the software switches platforms. But then we're not giving up. So we also continue to talk to the other platforms. For example, we talk to Intel guys at the SICOM conference. We start to meet and co-develop. And then we finally upstream this sketch-based approximate telemetry library into the Intel DBDK-based load balancer and become an internal product. And then we find that, okay, we're still not enough. We don't want this to be an internal product. We really want to benefit the open source community. And then we continue to work with DBDK maintainer, which is a data plan development kit, which is a popular high-performance network processing library used in all kinds of scenarios as well. And we talk to them and finally work with them after a year. We streaming and develop all this approximate telemetry capabilities and merge it into the Intel DBDK most recent major release. So it becomes the first of its kind that we introduce this ATS vision into one of the important high-performance networking libraries. So the lesson we learned of this journal is that this journey is that, oh, if we have a center like IUCRC or ISCO type of center, we continue to work with the industry closely, we will shorten this journey and then become more, building link, impactful, and upstreamable, deployable tools very well. So based on this kind of example, we wanted to propose two research routes. The first one is we want to pick one of the famous popular metric store for the system layers like Prometheus for how to enable the approximate telemetry system on top of it. So we carefully analysis. You can see this kind of boring system components, but I want to zoom in down a little bit here that across this Prometheus workflow, we will see, for example, when you deploy certain rules for running queries, you will see, oh, there's certain recompute over the data repeat again and again. And then it creates a bottleneck that query the final storage. It generates repeated requests into the backend storage, which all generates lots of performance bottleneck. Then it creates a large computing and storage cost. So to really enable that, we wanted to bring this large family store to be a low latency monitoring platform. It is possible because we can adopt this ATS vision. So we consider several optimization opportunities here. For example, we can bring in the in-memory sketch-based caching for query rules that we only need to, for data ingestion and data comes in as a string or the metric comes as a string, we only need to store some like sketch summary for the data. And then when you run the query, we don't need to, run and go back to the backend storage to repeatedly to query the data. And then we also can think about how to optimize the multiple queries and multiple alerts that has a large performance overhead. And how to do, for example, more efficient data source sharing between different queries and different data threads. We can also think about that without re-query and retrain over the data, that we can bring in the slide window query model that continuously monitor data and then continuously ingest new data and forget old data that can provide you with a continuous query maintenance that you don't need to rerun and re-query over time. So lots of such optimization will bring in to enable the Prometheus to support ATS. So a very quick example here. So we can, for example, this is a very high level time series data from Prometheus. You have the data comes over time, and then you have different dimension, just like a different color of dots here. So what we are building here is that we kind of summarize the data, like as the blue boxes here you see over time, and using an approximate sketch algorithms to run over and store a very tiny piece of data that would be good enough to support, for example, 95–99% of query accuracy over, for example, quantiles, top case, median, or other statistical queries you want to run them to understand about the data. And then that will kind of get rid of the repeated rescan over the data, and then get rid of the rescan over the overlapping data every time. And then the second steps we want to talk about after we enable this approximate telemetry system is we wanted using the telemetry for something. We want to use the telemetry system to enable fine-grained security applications. So one quick example here is economic denial of scalability attacks, or EDOS. So a very good example is called the UU attack. Is that instead of a traditional DDoS attack, you send a lot of traffic to certain containers, and then because of the auto-scaling mechanism, you might scale over multiple nodes, and you keep scaling up in terms of resources that finally eating up your cloud bills. But instead, if we can periodically generating the bursting traffic to cause the cycles of scale up and scale down, then we can still achieve a similar effect of this vertical auto-scaling with much lower cost at the attacker side, right? So this kind of security attacks is very hard to be detected, and we hope this more fine-grained, more real-time detection over Prometheus can be able to, together, for example, with the networking traffic, telemetry can be able to capture that. Okay, so we also think about another type of attacks that are targeting the resource sharing, or Ari.
The other, another application area is in side channels. Okay, where we've done a fair amount of work. So the classic side channels, many of them involve things like flush and reload, or page cache attacks that we worked on. One of the interesting things about page cache attacks is that it's not so easy to mitigate them. In fact, there was a patch that was instituted and then rolled back when Netflix complained that it was hurting their performance too much. And more recently, we've seen attacks on containers through the overlay file system. And so mitigation is kind of a problem. It's not really easy to do. And so the alternative to mitigation, if we can't do mitigation, those who can't do educate, those who can't mitigate, monitor. And so the question is, can we monitor systems at a lower level, operating system, kernel, whatever. Again, we're talking about very high frequency events, so we need some sort of sketching, some sort of way to compress the data, monitoring, for example, cache flushes, which are a key component of many of these attacks. You have to flush the cache in order to be able to identify what has been changed. Read times, page accesses, and the like.
So So you can see we are proposing over the telemetry techniques, over using an approximate algorithm and system libraries. We talk about summarize outcome and deliverables for this project. We are intent to deliver the open source approximate telemetry system library for Prometheus as the first step. We hopefully provide a few additional telemetry plugins for potential upstreaming. We also envision that we can develop open source monitoring tools for other platforms, as Ari just mentioned, for example, to monitor the kernel operations using eBPF and using the approximate based algorithm like Sketchin to compress the data and to support more frequent and more fine-grained operation monitoring. And third, we hope we can do the large implementation and evaluation over the real cloud deployment under iScale. Yeah. So in terms of the project benefits, we hope to, as I mentioned, hope to develop this, deliver these telemetry tools for easy adoption. We really hope we can co-develop with industry to fulfill practical requirements. You will see one preliminary successful example of streaming to DVDK. And then we hope this telemetry data sharing for the research community by doing the real cloud deployment. We're going to connect the real workloads, and then in a fine-grained manner that we hope to share this for the large community for research purposes. And very quickly, in terms of timeline, we hope we can be supported by 3-4 years, and including benchmarking, initial design, code release, and then also the platform demonstration and code development, etc. So we are a team that has expertise and experience over systems and algorithm and security. So we hope to, looking for 3 student support per year, and then do some summer research internships in the partner industry companies, and then, as mentioned, that to upstream our research and then do the code development. So this is real-time telemetry observability for cloud operations security. Thank you for your attention, and we're happy to take any questions.
Minutes for questions and review. Or just review and no questions.
Jokes, anyone?
About security, do you guys have a benchmark to evaluate the security attack, through the methods you guys are talking about?
Not yet. This is all in development. We have the attacks. We have benchmarks on the attack. We know what kind of rate you can exfiltrate data and things like that, but we don't have benchmarks on the defenses yet.
Yeah, we hope that during this project we enable this more larger scale real